This is the last set of notes over projectile motion, okay, going over type 3 problems. So this is a projectile that's actually launched at an upward angle from an unlevel ground, okay? So key features to this is it's not symmetrical, and so because it's not symmetrical, we can't use the shortcuts such as using half of the total time to find the maximum height. And we also can't use that the initial velocity is equal to the negative, or the final velocity is not the negative of the initial velocity. Okay, so just going through this diagram here, you can pause it and kind of write it down, but I'm going to kind of just go through some key factors. Okay, so we have a launched where we have our V1, which is the purple arrow there at the beginning. And then for the problems, you'll need to break down the V1 into its components, so into its horizontal velocity and its vertical velocity. Okay? Just like all the other problems, our horizontal velocity is going to stay constant throughout because there's no acceleration being applied to that object. Okay, unlike the vertical that has gravity acting upon it. Okay, the big thing here that's different is that there is a height above ground that we're starting at, and so that is equal to the drop to the ground. So if I was asking what's the distance it dropped to the ground, it would be just the height above ground. Okay, and then we also have the maximum height. Okay, a key thing to note as well is that here at this top point, we can set our velocity to 0. So here at this point, our y velocity would be 0 meters per second. Okay, because it's going in the positive direction, it's going up, the velocity is going up, and then it comes to a stop briefly before it starts going down and has negative velocity. Okay, and then we also have our range there at the bottom. Remember, that's our displacement in the horizontal aspect, right? And then very similar to our other ones, we have our final velocity there at the end of the arc, and it's also broken up into its components, okay? So just like before, we're going to have 3 variables that are in the horizontal aspect, and then we're going to have 5 variables that are in the vertical aspect, okay? So I'm not going to go through these. You can rewrite them down, but they're very similar to what we've done before. The big thing is that our initial and final velocity can't equal each other. Okay, we still have acceleration as negative 9.8. And just remember that delta time is the key thing that you should try to solve for first, because because it's a scalar, it can be used for both sides, both horizontal and vertical sides. Okay, so as far as problem solving for these types of problems, okay, first off, you can use the displacement of y as negative the height above the ground. Okay, and so why this makes sense is because our displacement is going to be downward from the height at which it was launched off of. Okay, so that's why we have a negative value there. Okay, and we can use this negative height in order to find delta t. So we'll actually use quadratic formula, and I'll go through the practice in this, but we'll first get in a standard form where we basically set the whole thing equal to 0. So then we'd have like an a squared, or ax squared plus bx plus c, okay? But in this case, it'll be delta t, and then we'll use the quadratic formula to solve for delta t. Okay, so I have that listed there. Also, we can find max height whenever we set our velocity to 0. So just like in the image up here, this point up here at the top is our velocity in the vertical aspect is 0. Okay, and then also when finding V2, we're going to be using Pythagorean theorem and tangent. Okay, so that's very similar to what we did in one of the previous problems. Okay. So to start, we'll want to draw and label the diagram, define the positive direction, and break our V1 into its components. Okay, so first off, defining the positive directions. I am doing my positive directions as up and to the right. Okay, I drew in my height because the golfer strikes a golf ball from the top of a 2.3 meter tall hill. So here is my 2.3 meter tall hill. The initial velocity of the golf ball is 28 meters per second, 45 degrees above the horizontal. So here I have that drawn in. Okay, so the next thing I need to do is break my V1 into components. Okay, so I basically just dropped down this to here in order to have a bit of room in order to break it up into its different parts. Okay, so we have our 28 meters per second is our hypotenuse, and it's 45 degrees. And we want to find Vx and V1y. So to find the Vx, it is adjacent to the 45 degree angle, so we're going to use cosine of 45 equals Vx over 28. So then times both sides by 28, and we get 19.7990. I rounded to 4 decimal places. Okay, and then to find V1y, it is opposite the 45 degree angle, so we're going to use sine of 45 degrees equals V1y over 28. Multiply both sides by 28, and we get 19.7990. I rounded that to 4 decimal places. Okay, one thing that you should notice is that they're both equal, and that's because we're taking it's for 45 degrees. And so sine and cosine of 45 degrees, they're going to be equal. Okay, the next thing that we needed to do was to list our variables. And so I did that here with breaking down the horizontal and our vertical. So we just calculated the horizontal velocity as 19.7990, and then also for the vertical we did as well, so I have that listed. Our displacement, remember, it's going to be in the negative direction because the object's going to be falling downwards the 2.3 meters. Okay, and then our acceleration due to gravity is going to be negative 9.8 meters per second. So just like the ones before, we don't have enough information for our horizontal aspect in order to start solving in that dimension. And so we just need to start with the vertical. Okay, so we'll start with finding the time, because remember, that's what you should always try to find first, because that is able to be used in both the horizontal and vertical aspects. Okay, so when finding time, you're going to use the vertical variables to solve, okay, using this formula. Okay, and a little bit different than what we've done before, we're actually going to set it all to 0 and rearrange it into standard form. And so we're going to kind of get into that, and then we're going to use quadratic formula to solve. Okay, so first let's plug in the variables into the formula delta d of y equals v1y delta t plus 1/2 a delta t. So we're going to have negative 2.3 equals 19.7990 times delta t plus 1/2 negative 9.8 delta t squared. Okay, so whenever I go and kind of like solve and rearrange this, I'm going to add the 2.3 over to the other side so that I'm setting the whole thing to 0, and then I'm going to rearrange it so I have t squared and then t and then basically no variable. Okay, so that we're setting it in that A, B, C standard form. Okay, So we're going to have 0 equals, and then our t squared is going to have negative 4.9 delta t squared plus our 19.7990 delta t plus 2.3. Okay, so this is going to act as our A for the quadratic formula. This is going to act as our B for the quadratic formula. And this is going to act as our C for quadratic formula. Okay, so over to the right, I have the quadratic formula written out for us. And so when we go and plug in all of our variables, we have delta t equals negative b, so negative 19.7990 plus or minus the square root of b squared, so 19.7990 squared minus 4a, which is negative 4.9, don't forget the negative, and times c, so 2.3. Okay, and then all over 2a, so all over 2 times our a, don't forget the negative, 4.9. So whenever you plug all of this in, we're going to get that delta t can either equal negative 0.113 seconds or delta t can equal 4.115 seconds. Okay, and so we're going to use the positive time. And the reason it gives us a negative time is because it's completing the arc. So if we look, it would be as if the time was from this point here. So it's before the launch. Okay, so we can't have negative time, so we're going to use the positive time. So our time for both is going to be 4.15 seconds. Okay, so now we can find the range. Okay, real quick, let me just highlight so that we keep track. So we found the time of the flight. The next part is the range. Okay, so to do range, we're going to use the delta t that we just found and plug it into the Vx equals delta dx over delta t. So our Vx is 19.7990 equals delta dx all over 4.15. Okay, multiply both sides by 4.15. And we get that delta d of x equals 82.1659. I rounded it to 4 decimal places, and that's in meters. Okay, so that is our calculated range. So let's go ahead and highlight that. Stay organized. Okay. So the next thing we're going to find is maximum height. Okay, so we're going to use our vertical variables, but we're going to set our v2y equal to 0 because this is our highest point, and in the vertical aspect, our velocity is going to be 0. Okay, and then once we find that, we need to just make sure that we include the initial height. Okay, so we need to add on the initial height, and so we're going to be using the formula that is highlighted here at the bottom. Okay, so let's go ahead and plug in all of the information that we have. So our v2y is going to be 0. So 0 squared equals our v1y, which is 19.7990 squared, plus 2 times our acceleration, 9.8, times delta d of y, our range, or our max height. Okay, so now we know that this is going to cancel out, and so we're going to get that delta d of y equals 20.000 meters. I guess there's another 0 there if I round it to 4 decimal places. So that is our max height from the actual launching point. So that is just the maximum height from here to here, okay? So we need to add on the 2.3, so plus the 2.3 meters that we already were above ground, and that's going to give us 22.3 meters as our final maximum height above the ground. So I'm just going to highlight that to keep it organized. So now the only thing we have left to do is find final velocity. So to find final velocity, first we're going to find our v2y, okay, by using our displacement in the vertical aspect as negative 2.3. And we're going to use the formula that's here highlighted. So let's go ahead and plug in our information. So v2y squared equals our v1y, which is 19.779 squared, plus 2 times our acceleration, which is negative 9.8, times our displacement, which we're going to be using negative 2.3. Okay? And so whenever we go through and we solve this, we're going to get that v2y equals plus or minus 20.9 meters per second. So I'm going to use the negative because our v2y, if we look at our original, it'll be below, it'll be down here. So I didn't really leave room for it, but it would be down here. We would have this as our v2y. So it would be downwards. So that's why it'll be negative. Okay. So that will be our v2y. We already know our vx. Our vx, remember, is 19.779. Okay, so if we put in the triangle, so we have our vx as 19.779, our vy as 20.9, we can find our v2, and then we'll need to find tangent as well. Okay, so using the Pythagorean theorem, we get that v2 squared equals a squared, so 19.779 squared. I'm actually just going to round this just for ease, plus our 20.9 squared. Okay, whenever we go through and solve it, we'll find that our v2 is equal to 28. Oops, made my 2 a superscript instead of a subscript. So our v2 is going to be equal to 28.79 meters per second. Okay, and then to find the angle, we're going to use tangent, and then we're going to do opposite over adjacent, so opposite of theta is the 20.9, so tangent of theta equals 20.9 all over 19.7, I'm going to just round 8, okay? So to get theta by itself, we're going to take inverse tangent of the 20.9 divided by 19.8, and we'll find that theta is 46.5 degrees. Okay, so our final V2 is going to be 28.79 meters per second, and it's going to be 46.5 degrees below the horizon.